we present PhysGraph, physics-based integration using graph neural networks. In this work, we demonstrate that it is possible to learn an effective physics-based integrator independent of the forces that are acting on the system. Our overall design consists of a force module which provides physics-based forces to the network. The network takes these forces and provides position updates for the nodes on the graph directly. Given the wide applicability of the method, we demonstrate the effectiveness of our architecture on the task of enhancing coarse clothing geometry by generating higher resolution geometry with physically plausible details. We train a single network using patch-based training data. During training, the network is only exposed to forces resulting from the thin shell potential energy modeling bending and stretching. Here we show a flip test result of our input and output to the network. The inset shows zoomed-in regions showing the added detail. Since the network has access to the forces acting on the system during inference, we are able to modify material parameters of the clothing fabric during the enhancement process to obtain art-directable results given a single simulation input. Here we show several combinations of the material parameters. However, the method is not limited to coarsely simulated geometry and works on other types of inputs as well. Here we show clothing geometry obtained from linear blend skinning, which we then upsample using PhysGraph. Note how the method is able to add detail and it is even able to recover from severe skinning artifacts such as the excessive stretching as can be seen in the armpit region. Even though our method is able to upsample skinning-based clothing geometry, the method itself does not rely on underlying skinning-based approach, and therefore, it works equally well on loose clothing such as this dress. We compare the convergence rate of PhysGraph with those of atom and gradient descent. We vary the learning rate for each and find that PhysGraph's performance is superior to any of the other optimizers. We now compare PhysGraph to related work. We compare with SSCH, SNUG, and the low resolution and high resolution output of PhysGraph. Note how SNUG results in collisions with the body geometry. Both SSCH and SNUG produce detail, but the detail does not change for different poses, whereas our physics-based detail varies with the pose. Finally, we show how our method performs on a simulated t-shirt sequence. Despite the fact that our method works on a per-frame basis, the generated detail is already mostly temporally coherent with the exception of areas with clustered collisions. As future work, we intend to additionally exploit temporal information to obtain even smoother results. To conclude, we present an effective approach to integrate physics-based forces using graph neural networks, which allows us to generalize to novel settings during inference. Thank you for your attention.